I found out that I was last here in this room 10 years ago, and then also 20 years ago. So it means that in 10 years, maybe I'll have something new to tell you. Okay, so.
1 second.
Okay, so before I start, these are people that I've been working on. What does this do? Oh. These are people I've been working on the subject. Way down, we heard already from Adi. Shimshon, Kalish, and Aviv Aroch are currently working on this project. Amikam Levi, we worked on this before. And previous generation here, Christiana Koch, which hopefully will come later today, Andor Toblina, Alon Bartanan, David Tanner, and earlier versions of what I'm going to tell you. So this is where we start. Any quantum system is open. So we know that and we try to forget, but I want to not forget about that. So here we have typical examples of what we have today: atoms in ion traps, superconducting qubits, Rydberg atoms, NV centers. Everything is influenced by the environment. And what I want to talk about today, I don't want to ignore that. I want to understand what does it do to us. So the issue is we want to control. So you can ask, what is quantum controllability of open quantum systems? And in this case, considering a model that I have a Hamiltonian that has what's called a drift part H0 and a controller, which has a time-dependent field on it. So there are mathematical theorems that tell us what is a condition on this controller operator to be completely controllable. And this paper here of Hung and Tarn, it's basically Tarn and Clark from 83, covers it. And it's an idea from Lie algebra that if we have this commutators of V with H0 have a full rank, they generate the U1 group, and it's completely controllable. So for closed systems, we have a very good, strong theory of what's called complete controllability. But if we make it an open system, we already know that this can't work, because what it tells us what we can do is unitary dynamics. But if we want to change a density operator, state to state from I to F, unitary dynamics will preserve the, you can say, the eigenstate. So if we want to change entropy or anything, this won't work. So if we want to you can say general, we want to change any state to any state, we need dissipation. So if controllability tells us something about that. And the other point, we want to control a process. So not only state to state, but we want to control the process. And what we really want to do, we want to go back to unitaries, but we know we're an open system, so can we control the system in such a way that to preserve as much as possible the unitary gate or a non-unitary gate? If we want to do a reset, it's a non-unitary gate, so we want to do it as best as possible or as fast as possible. So these are general tasks about controllability. And here, I kind of listed things about entropy changing control tasks. So the first one I mentioned here is what's called the Mapemba effect. And that is something I tried with my grandson. And the Mapemba effect goes like that. You want to freeze a popsicle as fast as possible. So this is what Mapemba did in Tanzania. So the question is, do you use hot water or cold water to do that? And the answer is counterintuitive. You use hot water. If you take hot water and try to freeze it as fast as possible, it freezes better than if you start with cold water. And since I didn't believe it, I tried it with liquid nitrogen I brought from the lab, and we tried it with my grandson, and at least one experiment proved that this effect is correct. It works. So you can control equilibration. You can make it equilibrate faster. So this is one thing. Then you can say general laser cooling is all problems of getting rid of entropy, so you want to change that. So laser cooling originally was a thermodynamic, was envisioned as a thermodynamic process, but it's mostly common. People think about it in different ways. And this is another example of entropy changing transformation. We want to do a reset to start our computer at, let's say, ground state of its ancillas or qubits. And you can say quantum annealing is also a problem like that. And then we can think about unitary gates and non-unitary gates, and I'll mostly concentrate on that. Okay, so what is quantum control? What's the difference between quantum control and, you could say, what's classical control? Classical control, I move on a trajectory. Quantum control uses interference. And the point about interference, our intuition is not good. It's hard for us to think about interference. It works, but to generate that. So what we want to do is quantum control. We start with an initial state. We want to get an objective. So the way to think about it, I want constructive interference and objective and destructive interference everywhere else where I do want to go. So the agent of control is coherence. So this is what you need for quantum control. So now if we add dissipation, I lose my coherence, and I need to move to equations of motion for open quantum systems. And this is, again, the setup is like that. I have a Newtonian with a drift, but I have to add dissipation to that. And so the dissipator degrades the ability to control. This is what we know, but it also helps us to do entropy changing transformations. Okay, so what's the physical origin of this dissipator? So you could say there are many origins, especially if we think about quantum computers. One is the pulse generator. If I want to do something, if I have a controller, it's always going to be noisy. So you can't do something, if hands off, there's no noise. I want to do something, I add noise. So we can think about, you can say, noise coming from the pulse generator. We can model it as Gaussian noise. This is what we do, and its dissipator looks like this double commutator. We have noise due to measurement, which you can think about back action. It also can be modeled by Gaussian noise, which is also this double commutator. And we have noise originating from the environment. Our system is not isolated. We have a system, we have a bath, and we have an interaction. So these are the main sources of noise that I'm going to describe. You could say they're all, to answer Vera, they're all physical noise. I don't introduce, you can, but I don't introduce artificial noise. Okay, so what we need is a model for open system dynamics. So we need to interact with the environment. I have a system, environment, and the system can change entropy. Okay, so we need a theory for that. And the theory that I'm going to use is quantum thermodynamics. And the theory is, the reason I built it like that is for a consistency reason. I want an equation of motion that's consistent with thermodynamics. In a way, I'm following Einstein, which did the opposite. He wanted, you can say that's how he invented quantum mechanics. He wanted a theory that's consistent with thermodynamics, and he found out the quantization of light. And so you can say it's between Carnot and Einstein, this is what we're going to use. So we need the theory that our quantum theory has to obey the laws of thermodynamics. And the point is that thermodynamics goes to any level. There's no macroscopic level. It goes to the lowest level, so our theory should go that way. Okay, So what typically you do, you take your Hamiltonian, you split it up to a system, environment, and interaction, and you say that this is sometimes called the church of the Hamiltonian. You say that altogether there's a unitary dynamics of the environment, and you do a reduced description of your system. So the unitary dynamics is driven by the total Hamiltonian. And then you look for the map of the system, which is called the reduced description, which describes the system dynamics. And we look for a differential form because this is what we need for our control. And so the question that we can ask is a dissipative dynamic independent of the unitary dynamics? And my answer already, I'll tell you, it's no. They're connected, and they have to be connected. So here's the system. And then the two steps that we take, one goes after what's called the GKLS equation, and here I have the picture of Lindblad, which starts with this idea by Krauss, which is a completely positive map, and which is always can be written in this form. And what Gurini, Kusakovsky, Lindblad, and Sudarshan were able to prove that the most general master equation has this form. And this is a mathematical theorem. It assumes that there is a global unitary transformation, and the initial state is tensor product. The first assumption, I think, is completely correct. The other assumption you can question. Can we always say that some initial state is a tensor product? But never mind, this is what needs to lead to this equation. So the reduced description under the Markovian limit always has this structure. And you can show that even you can go beyond the Markovian limit, the structure stays the same. It's always like that if you have a completely positive map. So it goes beyond even the Markovian limit. Okay, so what do we add to it? We add to this thermodynamic restrictions. We say, okay, we're looking for Markovian dynamics. We say the environment is large, it has infinite heat capacity, so its temperature doesn't change. And the environment is stationary. So if I look out, nothing happens outside. Now, the fixed point, which is a zero, is a Gibbs state with a system Hamiltonian. This can be renormalized, but let's put it like that. And then the final assumption that we're going to put here is what's called strict energy conservation, that you could say is a thermodynamic idealization, which says that the interface doesn't accumulate energy. So if energy leaves my system, it goes to environment and vice versa. I don't accumulate energy on the interface. Now, again, you can question that, but this is the assumptions we're going to do. And once you do these assumptions, you get restrictions on your master equation. And so this strict energy conservation, you can say that the commutator of the interaction commutes with a total Hamiltonian and also with a system plus environment Hamiltonian. This is how you state it, but this becomes a much stronger statement that says that the unitary part and the dissipative part commute. And you can look at it in a different way as a symmetry. What it means that the environment doesn't have a clock. So there's time translation invariance, which you can say is built into this equation. If I want to measure time, I can't use the environment. It doesn't have an oscillatory behavior or something like that. So the environment is stationary. So you can look at it as a time translation, dynamical symmetry, or strict energy conservation. And then this tells us what are these Lindblad jump operators inside the master equation. So they're eigenoperators of the free dynamics. You can say if I have two operators that commute, their eigenvalues, which in this case are eigenoperators, because this is Liouville space, are the same. So we can find a complete set of eigenoperators which span both the dissipative part and the unitary part. So when you work that out, you find out that these Lindblad operators, which I call LK and LK dagger, are eigenoperators of both the dissipative part and the free dynamics. So this tells us a great deal how to construct the master equation. And but this is not sufficient for what we want because we're looking at a driven system. Because we're looking for a control. That would be good enough for a static system. Now we have a driven system. So in order to describe that, what we have to add is a controller. So I have a system, Hamiltonian for a controller, and I have two types of interactions. And now all this in this purple circle, again, goes under unitary dynamics. So I can look for the general map, and now I can look for the reduced map of the system. And how can we describe this? We take this part, you can say, as a generalized system. So then I went back to the previous case. So I have my system and the controller and their interaction as a, can say, a device, a larger system. I can apply the same ideas that I had before. And now we can think about my controller. What is a controller? A controller is a large system again. And we can eventually will reach the semi-classical limit, which is just gives us a time-dependent pulse. But what does it mean? It's large, but non-stationary. That's the difference between the controller and the environment. The environment is stationary. The controller has to have coherence. And you can say there is even a theorem here. Coherence is a preserved property globally. Like energy is preserved, also coherence is preserved. So what it means, if I want to do something coherent, and I start from something stationary in my system and the environment, I have to have this coherence inside my controller. And what I do, I transfer this coherence to my system, and then I do coherent control. So this is how things are going to work. So when you work that out, you find I can work out, again, a symmetry that the global unitary commutes with this, you can say in the interaction picture, this system controller. And so it means it also commutes with a general map that I want. And you can go then to a semi-classical limit. And eventually you can show that the eigenoperators of the semi-classical system evolution operator, their eigenoperators consistent Lindblad jump operators. Now this is a little bit tricky because this evolution operator of the system is in Heisenberg representation. So you have to do the translation here from the Heisenberg to back. So what does it mean? It means that I can solve the free dynamics with a controller. I can find the evolution operator of my system. If I can find the evolution operator, I can find its eigenoperators, instantaneous eigenoperators. They'll become time dependent, which means I can now construct my master equation. So I construct my master equation from the free dynamics. So they're connected. So this is how this master equation looks. We call it non-adiabatic master equation, because in the adiabatic limit, these jump operators would be just the jump operators of the adiabatic limit, but they're not. Everything is time dependent. The kinetic coefficients are time dependent. The jump operators are time dependent. And you can see you get the jump operators from this equation. They're eigenoperators of the free evolution. And we have a fixed point, but we don't have an instantaneous fixed point. It becomes an instantaneous attractor. At each point in time, you can say there is a point that the dissipative part doesn't do much. So this is how we construct the master equation. I'll talk about it a little different later. And now, if we think about the attractor, instantaneously, you can think when I do dynamics, I'm going towards a target. This is dissipative dynamics. So typically it's equilibrium, but in this case, my target is moving, and the target can be, for a case of a qubit, can be again expressed as a generalized Gibbs state with certain operators. And, and this operator, this instantaneous operator, which I'm trying to move towards, that in a way defines the entropy generation. So the dynamics is dissipative. So I can calculate the energy dissipation, and you can find like Onsager relations of fluxes and forces in this case. So what you expect from this type of dynamics, if you move fast, you generate more entropy. You move slow, you're adiabatic, and then you're close to equilibrium all the time. So this is what you expect, and this is what you get from this type of equation. Okay, so now we have an equation of motion. Once we have an equation of motion, we can use it to do control. So again, the control we want to think about as either in states, which in this case are density operators. And this is the equation we want to control. So H generates a unitary dynamics, epsilon is a time control, and I have a dissipative part. And we can think about two classes of control problems. One is state to state. I want to go from I to F, initial to final, or process control. I want to find a control that will give me a whole map or a gate, and you can think about in quantum computing. Okay, so we need a theory, and what we adopt is a theory of optimal control theory. And what you do with optimal control, you define an objective, J. In this case, I want to, at the final time, optimize the operator A, the expectation value of A. So then you impose constraints. The first constraint, the evolution, is Liouville von Neumann equation. And you need another constraint, otherwise there are too many solutions to regularize a solution. Typically, this is what's chosen, that the field energy is minimized. So then you add two Lagrange multipliers for these constraints. One is on the Liouville von Neumann equation with a Lagrange multiplier B, and the other one on the intensity or the integral of the field, epsilon square on time. And you can say B is an operator Lagrange multiplier and lambda is a scalar. And then you do variations on J, which lead to your control equation. So you get a forward moving equation in this case for the density operator and a backwards moving equation for your Lagrange multiplier, which in a way tells, with initial condition of this Lagrange multiplier, is your target operator. So what you're doing is moving in two sides. You're moving from initial state with a density operator with your target backwards in time, and when they meet, you get out of that the control field. So you can say that instantaneously you're looking for the control field that will lead you from where you are to where you want to be. And where you want to be comes from the backwards propagation, and where you are comes from the forward propagation. So this is how this idea of control works. But now, if we want to do it for a process control, it's linear algebra. It's basically very similar in spirit. In this case, we need, you can say, a complete operator base in Hilbert space. So we have vectors that are composed of operators. And so we have scalar product between operators. And then a gate is defined by, you can say the gate is moving operator Y to operator Yj to Xj for all the set. So that's how the gate is defined. And so it's a multiple objective control problem. So we can write it in the same manner. We say that our objective J is the scalar product between the map that we want or the process that we want and the process that we get. So this is what we want to optimize it. And we can write it also as a trace formula. And then we know that our map is generated by the same equation of motion, by the Liouville von Neumann equation, and for the process. And we have two constraints. solution is a Liouville von Neumann equation. So this, in a way, is an upper level or Hilbert-Schmidt level of the same equation we talked about today before. And this last line is important. This is factorially more difficult in state to state. So this is where quantum complexity comes into. And the reason it's a multiple objective problem. So we want to do simultaneously all possible transformations from I to J, not one. So if you find all possible, they have to be orthogonal to each other. So each solution has to be orthogonal to all the rest. And that's why it's factorially more difficult than state to state. So computationally, this is a challenge. Anyway, so you can say we put everything together and we want to calculate, you can say the fields. We do functional derivatives to get the control field. And this is the equation that we need to do, and we can solve this, in this case, numerically. So out of the optimal control theory, we get an update for the field. You solve this iteratively, and you get solutions. Okay. So how does it work in practice? What do we do? We guess a control field, and we find a unitary solution, and we get the unitary free evolution. From that, we construct the master equation, which is consistent with this free dynamics. We calculate the evolution, utilize a final state, we can get the objective, and once we get this objective, we update the field, and we iterate until we finish. And we did it in two different ways. One is using the first strength of optimal control theory, using basically what we call Kosloff algorithm. And the other case is a version of CRAB, which only uses initial and final information. So it's less powerful. And I'll talk about that. So this is how you do it. You guess a field, calculate free dynamics, construct the master equation, solve the dissipative, and I see I lost some letters here. Never mind. Okay. And this is how you solve, you can see, the free dynamics and get the jump operators in one option, which goes like that. You solve, you get the unitary, you get the eigenoperators out of that. So this is one way. This method here relies on the inertial theorem. So we do it in the Schrödinger picture, and it's correct if you can do it in the inertial framework. But if you can't do it in the inertial framework, you have to do it differently. You do it through invariance. So what is an invariant? Invariant is a time-dependent constant of motion. It's an operator, which you can say its Heisenberg equation of motion is constant. It doesn't change. Its expectation value doesn't change in time. So we can write equations of motion for invariance. There are many. And you can say we choose the initial conditions for the invariance to be the projection operators of the Hamiltonian. So once we do that, we get, you can say, a linear equation for the invariant, which we can solve. So it's a linear equation, and we have very good propagators to do that. Once we have a linear equation to solve it, then here, this is the initial conditions, which we use these projections on the Hamiltonian. And what you can show that the jump operators are the commutators with every pair of invariants. So for every pair of levels, we have a Lindblad jump operator, which obeys this, you can say, eigenoperator equation. That's how we get sigma ij, the specific jump operator. But we also get the frequency, instantaneous frequency, which is built into the detail balance, instantaneous detail balance. So this frequency is an instantaneous frequency, and it's not the same frequency as the system. So this in general sums up, and now let's look at a few results. So let's do state-to-state control. This is cooling and heating on a block sphere. So what I'm showing you here, I'm starting at a point. Does this have a pointer? Never mind. I start here in the block sphere. So I either want to get to the origin, which is a completely mixed state, or to reach the surface. To go to the surface is cooling. To go to the middle is heating. And we use the same, you can say this Hamiltonian, with a control field. So one control field brings you to the origin, another control field brings you to cools the system down, and we can find solutions for both cases. So this works nicely. Now let's do a unitary. Do process control. In this case, this is for a simple case which I can show on the block sphere. So I want to do a Hadamard gate. So in Liouville space, it looks like that. This is a Hadamard gate or a reset gate. So I'm using the same control to do either this or that, the same Hamiltonian, the same dissipation. And you can find a solution that does Hadamard gate. So what do we see here? You see the surface of the block sphere is in this gray. That's where I started my red flag. That's where I started. And then I have a unitary trajectory, which is in purple, which reaches my final state. So I want to go from X, in this case, to minus Z. So the unitary without dissipation. So you can say it wanders around the surface of the block sphere until it reaches a solution. Now, if I add dissipation, I find myself, I have two types of errors. First of all, instead of reaching the South Pole, I reach Canada. You see the flag up there is Canada. So it's wrong. I wanted to go to the South Pole, be number one there. So this is if I just use a unitary. Now, if I use optimal control, that's the blue trajectory. I see I go from the equator to the South Pole with high fidelity, which I'll talk about differently. So what I can do, my controller fixes the dissipation. So this is really, how does it work? So there's a lot of dissipation. It's not, you can say the amount of power I put in is tremendous. So the entropy production here is huge. So it's not a, if you could say a decoherence-free subspace would mean I'm not touching the environment. It's not, it's the opposite. I'm cooling, I'm actively cooling my system. I'm allowing all the entropy production to be in the environment, and I'm not heating my system. So this is, in a way, how it works. The system entropy stays, you could say, low, or it heats a little bit. That's my errors. But most of it goes to entropy production, which you can see is orders of magnitude large. So this is, in a way, how it works. Another point about mechanism, what's interesting here, if I turn off the dissipation and use the solution, it still gives me a relatively good unitary solution. So you can say what my control did, selected out of all possible solutions, a unitary solution that you can say sheds away or cools the excess heat into the environment. So you could do a 2-qubit gate. Again, this works on a similar case. And you can see, again, it works on a similar principle. So, but I want to move to another type of noise, which is noise originating from the control. So this is typically ignored. When you say, I want to do a controller, there's a price, because a controller is always noisy. And it's not only noisy, it has Markovian noise, because there's always a fast component. If I want my controller to do something, it has to be fast relative to what I think about. So slow noise, we can calibrate. But fast noise is hard to fight. And this case, we use a Gaussian model, which is, I think, appropriate for this type of problem. And you can say that I can have either what's called amplitude noise, which is, you can say if my controller here is X, so it gives a double commutator with X, or phase noise, which is timing noise, which is more harmful, and which becomes a double commutator with a time-dependent Hamiltonian. So you can say amplitude noise, if this is my signal, I do errors on my amplitude, and phase, my step machine, which determines the timing, has stochastic errors, and I get that wrong. So I get the timing wrong. So these two types of errors we can simulate, and the question is, can we fight these types of errors? And this is again a Hadamard gate, and this is phase noise. And what you can see, first of all, here, this is the unitary. I reach my target on the surface, and if I add dissipation, I go to an inner sphere, which means this is all decoherence, the difference between the two spheres. So I don't reach to the target. Now, if I add a controller, I can bring myself back. But if you look at the solution, it doesn't look like the unitary solution. It looks different. It takes me through a different trajectory. And if you look closely at the one to the right, you see that I reach my target. So I can mitigate these noise by choosing the correct control. So not any field does it, but if I choose the correct field, I can mitigate that. And here's how the control field looks like. You can see I have a guess field, optimal control. You can say updates it, and you get a field. Just looking at that, you don't get much idea. But this is for noise reduction. You can see this is the logarithm of the noise reduction. In this case, we get, for a single qubit, we get maybe a factor of 2 or 3 of noise reduction. And this is the dissipative strength. So this is what we get, and it's always better. This is the noise reduction for amplitude and phase noise. Now, if I want to do better, so I have my single qubit gate, and I want to do better. So what should I do? The answer is add another qubit. Do a single qubit gate with two qubits. So this is what we do. We added an ancilla. And you can see immediately the noise reduction went orders of magnitude. I can fix my gate by 4 orders of magnitude. I can get rid of the noise. How does it work? I move population to the ancilla. You can see if it's more noisy, I move more population. Here, this is in percentage. So don't move much, 0.1%, 0.2%, but that's enough. So basically, I move the noise to the other bad guy. And I keep my gate quiet. I'm finished soon. Okay, this is noise mitigation on a C0, again, a 2-qubit gate. Again, on a 2-qubit gate, you can do much better. So we can do orders of magnitude better. And here's my conclusions. What I wanted to talk about is open system control. And the first point is that the dissipative and the unitary generators are linked. So we can't think about them separately. And we identified control mechanisms. So fast reset or Mapemba effect. And you can do active cooling while performing unitary tasks. And what was surprising to me that we can fix the fidelity of gates by orders of magnitude by doing optimal control, much more than I expected. So here are some papers. This paper appeared. This will appear in Quantum. And this paper, and here is the talk that I gave 20 years ago. And you can say, maybe I didn't change at all, except I added open systems. So I still talked about unitary, but that's it. So thank you.